Memory is an essential component of a von Neumann computer. Storage allows us to keep data and programs. A memory read occurs in several steps. The access refers to an address in the memory device and specifies the transfer direction as read. The memory device reads the requested location. The data is supplied to the memory device interface. A write follows a slightly different sequence. The access refers to an address in the memory device and specifies the transfer direction as write. The data to be written is provided to the device. The memory device stores that data value in the access location. The memory device acknowledges the completion of the write operation at the interface. The von Neumann model couples a central processing unit in memory. Memory holds instructions for the computer and data that programs operate on. The development of a useful and scalable random access memory took several decades, culminating in the semiconductor random access memory, or RAM. Here's a simple model of memory. An access can be a read or a write. The R/W bar signal controls the direction of the access, read or write. An address specifies the location to be accessed. Data is provided in the case of a read and produced in the case of a write. Data is provided in the case of a write and produced in the case of a read. Memories typically use bidirectional connections for data. Memory is organized around a two-dimensional array of core cells. A row is selected by the address. The address may also specify a subset of columns. A bit line runs vertically to either read or write the selected row. We use two different types of memory. Static RAM, or SRAM, is faster. It's larger, meaning that fewer bits can be put in a given space. It also requires a power supply to maintain its value. Dynamic RAM, or DRAM, is smaller, meaning that more bits can be put in a given space, but accesses are slower and its values can decay over time. Here's a schematic for an SRAM core cell. The bit is stored in a pair of inverters connected in a cycle so that they reinforce each other. Pass transistors are controlled by a word select line. These pass transistors control access to the inverters from a pair of bit lines, true and complement. To read the cell, we open the pass transistors and let the inverters drive the bit lines. To write, we use the bit lines to override the inverters and flip the value in the cell if necessary. Here's a schematic for a one-transistor DRAM. The bit value is stored in the capacitor that's fabricated using a specialized process. A single transistor controls access to the capacitor from the bit line. The DRAM cell is much smaller than the SRAM cell because it has fewer components. But because it doesn't have any circuits to amplify and regenerate the state, the value can decay over time. DRAM requires refreshing, typically about once per millisecond. Given the trade-offs between size and performance among memory components, we use a memory hierarchy to create an efficient memory system. A cache is an SRAM that we use to hold a few of the values from the larger DRAM. This memory system includes two caches, one for data and another for memory. The SRAM can't hold copies of everything in the main memory, but it is considerably faster. We can use specialized logic to manage the access process and make sure we get the values we need. The simplest form of cache is direct mapped. Here's a UML sequence diagram for a memory access with caches. The memory access logic first checks the cache. If the requested value is in the cache, the access is performed there. This is known as a cache hit. If the value isn't in the cache, the request is satisfied using the main memory, resulting in a cache miss. We can calculate the average access time for a memory given a hit rate, the probability that an access will be available in the cache. We can determine the hit rate for a set of programs experimentally. The access time for main memory and the cache are design parameters based on circuit and logic characteristics. The average access time is calculated from two cases, a cache hit and a cache miss. The probability of a cache miss is 1 minus p hit. The simplest form of the cache is direct mapped. A direct map cache is divided into a set of blocks. The capacity of the cache is given by the product of the number of blocks and the size of the data field in each block. An address is divided into 3 fields. The index determines which block may have the desired location. The contents of that address are checked, and the tag in the block is compared to the tag value given in the upper bits of the address. If they match, the result is a hit. The data field of the block may contain several units of data, and offset can be used to select the desired block. The offset may be used to identify the desired data in the block. Here's an example of cache operation for a simple 4-entry cache. At the beginning of the loop, none of the instructions for the loop are in the cache, so accesses take tmain time. The loop may iterate several times and take advantage of the instructions being in the cache with an access time of tcache. When it exits, the first instruction of the exit replaces an instruction in the cache, in this case index 2. The access time for the exit instruction is tmain. Many computers use several levels of caches. The first level cache is generally both the smallest and fastest. At higher levels, the cache becomes larger and slower. This trade-off between the size of a cache and its speed is due to the fundamental characteristics of the MOSFETs and the circuits. Providing a hierarchy of caches at different size performance points allows us to better match the memory characteristics with the demands of programs running on the CPU. The second level of the cache is unified and holds both instructions and data. A memory access first checks the level 1 caches. If it can't be satisfied by level 1, it's passed to the level 2 cache. If the request can't be satisfied by the level 2 cache either, it's passed along to main memory. SRAM is used to build register files in data paths. The SRAM structure provides fast register access times, critical for fast data path clock speeds. SRAM also supports multiple parallel accesses thanks to multi-ported RAMs. The row logic is controlled by the register file select signals. A register file uses several bit lines, one for each parallel port. Flash memory has become the predominant form of semiconductor storage of data for long periods without power. The basic architecture of the flash storage device is similar to that of dynamic RAM, but it makes use of different devices and circuits. A floating gate transistor includes 2 gates. The upper control gate takes advantage of quantum mechanics to write a value into the floating gate. The floating gate then controls the channel and whether it conducts. Modern flash cells use advanced circuit techniques to store more than 1 bit per cell. Writing a flash requires first erasing it to 0, then writing to 1 if necessary. Flash cells can't be erased individually, so a block of flash is erased, then rewritten. Thanks, folks.